So, good morning. How many of you had a chance to take a look at your molecule for the analysis and start identifying the functional groups that are in it? Yeah. A couple of wavy hands, which is good. One that's already been submitted and graded. You don't have to work too hard on it, but the one that I did get was laid out really well. So just for reference, they used some different colors to circle the specific bonding groups that represented the functional groups, and then they labeled them. I'm sure that helped them feel confident that they had nailed down all of the functional groups, but you don't have to do any annotations. If you just have your picture and then underneath it you say, this has a ketone, an amide, an ether, an alcohol. That's really all you have to do. And remember, I'm going to give you pass-fail. Yes, you've got all of them. No, you don't have all of them. Or you have some that are not actually in the molecule. So feel free to do it how you will, but all I need to see is the list. Does that sound good? Two topics that we're going to be covering as we move through this unit. We're going to cover them in quite some depth, but the terms might not feel so evident. We're going to be looking at regiochemistry, and we're going to be looking at stereochemistry. So I want to get these ideas in your head so that you're thinking about it through these next couple of weeks. When you hear a term like that, regiochemistry, what do you start thinking? Location, regions in a molecule. So we kind of already talked about how different atoms bonded in different ways is regiochemistry. But yeah, we're really just saying how a molecule is structured at any given point. So look at this carbon atom. How is it bonded? That's its regiochemistry. I think it would be fair to say that functional groups fall into this idea of regiochemistry. What is that atom bonded to? How is it bonded? How many other carbons are bonded to it? Today, an important topic that we're going to learn there is degrees of substitution. And this is one of our learning objectives for today, which is describe the regiochemistry of alkane functional groups. The other topic that this unit really dives into is stereochemistry. And I think I talked about stereochemistry yesterday, but I'm curious from your perspective. Do you remember what it means or what we're trying to say with stereochemistry?
So it's something that's the same, but it's in a different place in space.
Different place in space. So does that mean like how our planet kind of moves through space in that way? It's just like moving from here to here? Miyura?
I think we're kind of putting like if it's coming towards us.
Okay, yeah, so things coming towards you versus things going away from you. So the connection between what Russ and Miyura said is space, spatial arrangements. And that's a good idea. Stereo there. Hopefully you guys are thinking something like stereo surround sound. I can't actually think of anything else that means stereo. We're going to identify a term in this unit that's called sterics. And sterics comes back to stereo. Stereochemistry refers to how these molecules take up space. We could also maybe call this spatial arrangement. Now, today we don't have a learning objective on stereochemistry, but that's going to be a really major part of what we do. Instead, our other learning objective for the day, in addition to describing the regiochemistry, is to be able to evaluate nomenclature. And I think we could say that evaluating nomenclature actually falls under regiochemistry, because you are describing how the molecule is structured, what is connected to what, and in what ways. You all have learned nomenclature before. When you took general chemistry, you learned the nomenclature of ionic compounds. You don't use prefixes. You name the compounds based on their valence charge. You learned about the nomenclature of transition metals. Some metals have multiple oxidation states, and they require those Roman numerals. You learned about nomenclature of binary covalent molecules, and how the prefixes become crucial to predicting how many of which of them are there, because they're not balanced by charges. So nomenclature is a system of naming, and we're going to be looking at organic nomenclature today to make sense of that. All right. So we're going to kick off with the regiochemistry of alkanes. We're going to talk about carbon substitutions. Sometimes it's better to think of it as degrees of carbon substitution, because we're actually going to analyze reactions later in the semester that are called substitution reactions that happen to our carbons. So this term substitution is going to be used in different ways. I want to make sure that we can differentiate them. Degree of carbon substitution. It depicts how many carbons any given carbon is bonded to. Now, the first degree of substitution is being bonded to 0 other carbons. This is simply referred to as a methyl carbon. We're going to talk about nomenclature in a minute. Methyl is a part of that nomenclature. Meth refers to just one. And the YL, the ul part, actually just refers to being a descriptive rather than definitive. So methyl, meaning just one carbon. And let's look at some examples. CH4 is a molecule called methane, and CH3OH is a molecule called methanol, also called methyl alcohol. Substitute that OH for any other group, you've got a methyl carbon. You've got just one carbon, it's not bonded to anything else. Let's talk about a carbon that's bonded to one other carbon. This is called a primary carbon. And it's represented with this degree symbol, first degree, 1 degree. Now, anything that is just a carbon group doesn't contain a primary carbon. So we need to start expanding our structure. And we can go from very small to very large and see primary carbons. So here's a compound called bromoethane. And bromoethane has 2 primary carbons. Both of those carbons are bonded to one other carbon, each other. But let's take it to a bigger molecule. Let's look at something a little bit more fun. Let's take an aromatic ring, and we'll draw a ketone. There is only one primary carbon in this structure. There's only one carbon that is bonded to one other carbon. Right here. Now, what's confusing is that this carbon, this primary carbon, we'll later refer to it as a methyl group. We won't describe it as a methyl carbon, we'll refer to it as a methyl group because it's a CH3 group that's connected to something else. So there is kind of this scaled up relationship between its degree of substitution and what you call it. Methyl carbons are not methyl groups necessarily. It's tricky waters. All right, 2 carbons. What do you suspect we'll call this? Secondary. And we'll abbreviate it with second degree. If we take a look at isopropyl alcohol, isopropyl alcohol has 1 secondary carbon. You guys all know isopropyl alcohol, yeah? Trying to give you some relevant compounds while we're at it. And again, we can expand this and we can start looking at some more complicated structures. So let's take a look at this alkyl halide structure. Now the name for this is a lot more complicated, so I don't want to bother us getting into its name, but how many secondary carbons do you see? Raise your hand if you see 1. If you see 2. If you see 3. And 4 would be the maximum. All right, let's take a look. Here's a carbon. How many carbons is it bonded to? Just 1. This is a primary carbon. Are there any other primary carbons? 2 others. The other CH3 groups are primary carbons. Okay, let's move in from the left. Here's a carbon. How many carbons is that bonded to? 2. So this is a secondary carbon. We would actually refer to it as a secondary alkyl halide. In a similar way, we would call this a secondary alcohol. And here, we would call this a secondary alkyl halide. So we can actually infer that being bonded to a heteroatom doesn't change the degree of substitution, but it does have other atoms besides just carbon by saying it's not just a secondary carbon, it's a secondary alcohol. It's a secondary alkyl halide. Moving to the right, how many carbons is this bonded to? 2. So this is a secondary carbon. Moving one more to the right, how many carbons is this bonded to? 3. So this is not a secondary carbon. neither is it a primary carbon. Now, I gave you guys this idea that primary carbons are often referred to as methyl groups, or those CH3 groups is referred to as methyl. These CH2 groups, like this one here, a secondary carbon, this is referred to as methylene. It's a methylene group. I don't love it, because that ene at the end makes you think alkene. There's no alkene here. But it is saying that this carbon is bonded to as many other carbons as maybe an alkene would be bonded to. I don't know, it's a bit odd, but that is kind of the terminology. This carbon that's bonded to 3 other carbons, what would we call that? Tertiary. 3rd degree. Now here's a great example. This is a compound often called tert-butyl bromide. What does, oh sorry, I haven't taught you that yet. Butyl is referring to the fact that there are 4 carbons in this structure. We'll make more sense of that when we get into the nomenclature. Butyl is telling us 4 total carbons. I see it, 1, 2, 3, and then the 4th is at the center. What is tert trying to describe? That the connection between the 4 carbons and the bromine is at a tertiary carbon. Specifically in this case, we've got a tertiary alkyl halide. So we'll call this our tert-butyl group. What other degrees of substitution are present in tert-butyl bromide? Sorry, I really just blanked. Yes, primary. 3 other primary carbons in tert-butyl bromide. Let's look at one more example. This compound has 1 tertiary carbon, and that tertiary carbon can be abbreviated by, it's a CH group with 3 other bonds going to it. What do you suppose we call this one? Got a methyl group, CH3, methylene group, CH2. So I heard the 2 options, methylane or methyline maybe. And the idea is, yeah, because it's bonded to 3 other carbons, where it's got 3 bonds to other carbons, that's very similar to an alkyne carbon, having the triple bond to another carbon. And so this group can be referred to as a methyne group. But notice how it's spelled. It's not methine with a Y. It's methine the way you'd expect it to be spelled with an I. I was not in charge of nomenclature. If I was, I would have picked some other ideas. There is a challenge. Oh, I'm sorry, we're not done yet. Getting ahead of myself. How many bonds can carbon make? So how many possibilities are there for bonding to other carbons? A total of 4. This one we call quaternary. I always have such a hard time spelling it. Quaternary. Those of you familiar with biology might recognize this term from how proteins interact with other proteins. they wrap around themselves in primary interactions. Then those wrapped around parts interact in secondary interactions. I always forget what the tertiary is, but a quaternary interaction is different proteins interacting with each other. Am I wrong? I think hemoglobin is a great example of quaternary interaction. Let's do an example. I've got this aromatic ring, and then I've got this 4-carbon group connected at one central carbon. Do you guys see what that group reminds you of? It reminds you a lot of this group up here. And so this molecule is referred to as tert-butyl benzene because it's got those 4 carbons connected at a central carbon to the benzene ring. But what's misleading about that is just what is equally misleading about this. This is considered a methyl group, even though it's not a methyl carbon, it's a primary carbon. This is considered a tert-butyl group, even though this is not a tertiary carbon. How many carbons is it bonded to? 4. This is a quaternary carbon. It's horrendous, the way that they have given names based on how many carbons it is attached to, and then when it can attach to other carbons, they still kind of identify it by that signature bonding characteristic, arrangement of atoms. All right. There is kind of a caveat to all of this, which is we don't use this terminology on alkenes or alkynes. And I mean, I've abbreviated that to say sp2 or sp, and that's because if you look at this ketone, you have an sp2 carbon, and you could say that it's a secondary carbon, but it would be more meaningful for you to say that it's a ketone than calling it secondary. If you look at the aromatic ring, sp2 hybridized carbons, we often don't look at these carbons that are in double or triple bonds and try to define how many other carbons it's bonded to. And I'll try to point out the reason. This carbon is bonded to 2 other carbons, but it's bonded to other carbons 3 times. It's got 3 bonds to carbon, but it's only bonded to 2 carbons. And the whole point of degree of substitution is to describe how many other carbons it's bonded to. So there's a bit of a falling out when it comes to, is it a secondary because there's 2 other carbons, or is it a tertiary because it has 3 bonds? And luckily, we don't really compare how sp2 or sp hybridized carbons are bonded to how sp3 hybridized carbons are bonded. We usually compare sp3 to sp3. And then we can do other things to compare sp2 and sp2. Let's take, for example, this molecule. This molecule has both an alkyne, carbon-carbon triple bond, and an alkene, carbon-carbon double bond. Now, we might not use the terminology here of primary, secondary, tertiary, etc., but I can still say that this carbon is more substituted than this carbon. We can still apply the regiochemistry. One carbon is more substituted than the other. One carbon is bonded more times to other carbons. And we can do the same thing on this alkene. This carbon on the left is bonded to more carbons than this carbon on the right. So we're not going to try and use terminology here to say the one on the left is a quaternary carbon and the one on the right is a secondary carbon, because it just doesn't fit well. But we can still approach regiochemistry in a similar way to say more substituted, less substituted. And what we're describing is how many bonds to carbons it has. Are you guys comfortable with that? Let's see if we can apply it. I'm going to put a molecule up here, and I would like you guys to go through and identify how many of each type of molecule, or of each type of carbon are present. Yeah, I think that's okay. Oh, I'm gonna add something to it. Sorry. Just thought of this. I'm adding this little OCH3 group. Where's the carbon that this corresponded to? There you go. Did you do that? Where's the carbon that this corresponded to? It's not, right? Yeah, because that's too far away. Yeah, you can definitely use that to abbreviate, which is good. Those look good. Looking good. I think you're missing two CH3 groups coming off the top of this carbon. You see that? Mm-hmm. Off to this one. No double bond. Just one bond. Where's the carbon that this carbon is bonded to? There you go. Yeah, this one, this one, and this one. Those two. But those aren't good.
Okay, yeah. I just want to see if that's good, right?
Yeah. Yeah. And then we want to analyze this one, these two. Mm-hmm. Anywhere that there's a carbon, we want to try to describe it. Mm-hmm. This one will be the most unique though. Mm-hmm. Good. Yes. Great. Yeah, you got it. So far, so good. I like the tally. It's hard for me to. No. I don't have the numbers down in my head, but I think you probably right. Sorry, bro.
A little better.
Yeah, and then we could abbreviate it as. People have been using different things to label the one that's off by itself. We'll talk about it though. Good. Yep. Doing great. Off to a good start. So, are we putting here at this carbon? Would you agree that this carbon is bonded to the two other carbons in the ring and to these two CH3s? Good. All right. So let's pull together and analyze this together. How many methyl carbons are in this structure? Carbons that are bonded to 0 other carbons. There's one. And I actually forgot that I could even do that in a molecule. That's why I went to add that one at the end. Because I was going to say, you can't have a methyl carbon and have it be in a structure. But we can. This CH3 is bonded to an oxygen, which means it's bonded to 0 other carbons. So we have one methyl carbon. Now, when it comes to primary carbons, there's a lot, yeah? We've got primaries at all of these ends of the carbon chains. So 1, 2, 3, 4. Am I missing any? Secondary carbons. There's also quite a few of those. Anywhere that there is a carbon bonded to only 2 other carbons. I think the most confusing ones here for the secondaries would be this secondary alkyl halide. You can't count the bond to bromine as a degree of substitution. That's why we call it a secondary alkyl halide rather than a tertiary carbon. It's not bonded to 3 carbons. It's bonded to 2 carbons and a halogen. And then similarly, right opposite it, secondary ether, connected to an oxygen, but only connected to 2 other carbons. So that's 1, 2, 3, 4, 5. Tertiary carbons there are less of, and they're actually right next to each other. Here's a tertiary carbon in this little group that comes off of this ring. And then here's a tertiary carbon in the ring that connects to that group. What's funny is that this little group right here, we're going to learn to call it sec-butyl, similar to tert-butyl, but indicating a secondary carbon. Because you can see that as a group, this carbon here is only bonded to 2 other carbons. But then when you put that group bonded to the rest of a molecule, it becomes a tertiary carbon. So we call the tertiary carbon sec, and we call the quaternary carbon tert, and we call the primary carbon methyl. Quaternary carbons, we've only got 1. So 2 tertiaries, 1 quaternary.
Why is it called substitution? Like, what are we substituting?
Great question. What do you think?
Carbons
You're substituting carbons?
for other carbons?
Well, but that implies that you're starting with a carbon and then you substitute it for a carbon. I think a good way to think of it is, here is your smallest organic molecule, the base organic compound. It has a carbon only bonded to hydrogens. Now, substitute a bond to hydrogen for a bond to carbon. And that's where we get the idea of carbon substitution. I've removed a hydrogen, substituted that hydrogen with a carbon atom. Now it's a primary substituted carbon. Remove 2 of those hydrogens, replace them with bonds to carbon. I've got a secondary substitution. And it's not a bad thought process to say, why don't we say I removed a bond from hydrogen and replaced it to a bond to bromine? Isn't that substituting the hydrogen for a bromine? Substituting the hydrogen for an oxygen? It is. But that is not what's being implied with carbon substitution, which is why we use those descriptors then to say secondary alcohol, secondary alkyl halide. So by describing the functional group, we do kind of explain what other hydrogens have been removed and substituted, but we prioritize degree of substitution looking at bonds to carbons. Are you okay with that?
Yeah, thank you.
All right. Maddie?
Can you explain when and why we would use those last couple weird, like, for the primary, it's methyl, and then for the secondary, it's methylene. Like, when would we?
Yeah, honestly, in my class, I don't think you will use it much.
Okay.
But it can be a useful way of pinpointing a region in a molecule. For example, we're going to learn reactions that are regioselective. They only react at the most substituted carbon. So then you have two ways of saying it. Look for the tertiary carbon, that's where it will react. Or you could say, look for the methyne carbon, that's where it will react. Another way to think about this, because our functional groups can be described by the degree of substitution of the carbon, then we could have a tertiary carbon that doesn't have a hydrogen because it's a tertiary alcohol or a tertiary thiol or a tertiary ether. Or we could have a methyne carbon because it's tertiary and it has a bond to hydrogen. So if you didn't want to go through the process of saying tertiary ether or tertiary non-functional group, tertiary alkane, then you could just fall back on saying it's a methyne carbon. But yeah, to be fair, I won't use it a lot. I'm putting it out there so that if you guys see resources on the internet that refer to it, you kind of get an idea of what they're trying to get at. Yeah? It's another perspective on the naming of it too. Other questions before we move on? Do you guys feel comfortable with these? They're straightforward enough. It's not really a challenge, but it takes practice. So as a reminder, go down to the old study materials at the bottom of our Canvas page. I have some resources on alkanes where you can go in and look at labeling degrees of substitution. There's an old homework problem set that has that. All right, well, I want to transition now into nomenclature, especially since I've already kind of teased you with some of the nomenclature ideas. What does this prefix mean? Why is this suffix YL changed to ane or ane all? Why do we call this tert butyl? Why is that YL coming back around? Full transparency, last summer I was going through an interview process to become a tenure track faculty here at SLIC, and I had to do a teaching demonstration. And the topic was given to me 24 hours in advance on organic nomenclature. And I was so excited. I have always wanted to revamp the way that I taught nomenclature, and then that was just the push to get it done. So this is a revised version of the activity that got me my job last summer. And here's the idea. This is what I tried to pitch in my demo. These are two fairly common compounds. In fact, I think one of you is using sorbitol as your molecule this semester. Yeah. The name sorbitol doesn't give you a lot of indication of its structure. Would you agree? If I told you to draw the molecule sorbitol, would you draw a 6-carbon chain with an alcohol coming off at each point? You might have an idea that there is an alcohol because of this little OL at the end. Kind of sounds like alcohol. 6? You'd never know it. And this is Freon. You guys know what Freon is useful in? Air conditioning. So you compress Freon. It doesn't have great intermolecular forces. You compress it into a liquid, and then you run it past something hot, and it steals that energy, endothermic process for itself. It steals that energy to become a gas, which it likes to do. Freon 112. Can you draw its structure? What? You'd never be able to guess that it's a tetrachloro-difluoro compound, right? Why would you? So, systematic naming. This is what our nomenclature does, and we're following IUPAC nomenclature. You guys know what IUPAC stands for? International Union of Pure and Applied Chemistry. Talk about sitting on a high horse, right? So this is their system of naming. Their systematic naming removes any ambiguity. And it clarifies structural connectivity. You don't have to guess about what atoms are connected to what atoms or where along a carbon chain a certain functional group appears. There's no ambiguity. The purpose of nomenclature here is to be as redundant as possible to make sure that there is no room for error in explaining that molecule. Now, when we go through this, I thought I pulled up the PowerPoint and I didn't. It is a PowerPoint. I'm just going to open my PowerPoint. As we go through this, we're going to look at nomenclature one piece at a time, and we're going to do some practice problems on a set of molecules over and over again. So when we get to that first set of practice on those molecules, if you're not using a downloaded version of this PowerPoint, then I recommend you just draw them once and leave space to do several practices underneath them, applying each part of the name. I actually don't remember if there's no transitions in here. So, all right, starting off, a name is best formatted with these four parts. A name has a prefix, a root, a locant, and at least one suffix. And as we'll come to find out, for a lot of names, the prefix takes up most of the molecule's name. The root, locant, and suffix make up the smallest part of the molecule's name. And within the prefix, you can have multiple different things listed that each have their own locant and suffix. So we'll tackle these first by looking at the roots, then the suffix, then the locants. And then we're going to come back and basically apply all of those things again to our prefixes. All right? So starting off with root. We say that a root describes the parent chain. And the parent chain is decided as the longest carbon chain. Caveat, containing a principal primary group or a primary functional group. So you can see we can't really get into nomenclature until we know our functional groups. And we're going to talk about the next page, what are the primary functional groups? How do you prioritize those groups? So we're going to I'm going to demonstrate basically all of these things again on the board. If you've got this printed out, you can kind of just fill in what's missing. So we'll look at the carbon chain, what it looks like, and then what its name is given. It's the root that we call it. A carbon chain is just one carbon long, which is very challenging to do a bond line structure for. Then this is given the root meth. And you've seen that root already, both in methane, methanol, and methyl. That prefix, meth, tells us one carbon. You guys also know colloquially meth, short for methamphetamine. Now you can interpret that there is a one carbon chain in the molecule methamphetamine. That's why it gets its name. 2 carbons. Now this we could draw as bond line. It looks a little clunky though. So it's sometimes easier to represent this as well in kind of a condensed format or Lewis. Confusingly, 2 carbons, F. You might find mnemonics that help you memorize this order, like my elephant prefers butter or something, I don't know. But you get familiar with these the more you go through them. 3 carbon chain. Now, this is very common to draw with bond line, but it is important to recognize it doesn't need to be just alkane. You can have functional groups coming off of this any which way. Prefix, prop. What do you guys think of when you hear prop? Propofol. What else? Propane. I'd have to look at propofol again. I can't remember if there's a 3 carbon chain in there. I actually only just heard about it this semester because about 4 of you guys submitted it in my Ocam 1 and Ocam 2. But I think of propane, which is a 3 carbon alkane structure. 4, butane, or excuse me, bute is the root given. Those 4 are the least familiar to you. If you've taken a math class, you've probably seen all of the other ones. 5, 6, 7, 8, 9, 10. I doubt that we will get up to 10 in our class. In fact, I rarely give structures that are even 7 or 8 carbons long, but I want you to recognize that you know them. 5 carbon chain is pent. A 6 carbon chain is hex. A 7 carbon chain is hept. 6 and 7 are the 2 that I think you might mix up for the other prefix list. This, I think, is Greek, hex and hept. The Latin is sext and sept. So I just want you to pay attention that we're using the Greek naming here, hex and hept. 8-membered chain. It's really hard to keep track of all those carbon chains. Oct, like October. 9 carbon chain, non, like November. It's worth a shot. 10, dec, like December. We are not just going to look at linear chains. We're also going to look at cyclic carbon chains as well. And again, I'm not going to have you guys draw anything past an 8-membered ring. I probably won't even have you ever draw a 7 or 8-membered ring. They're hard to draw. They're hard for me to draw. And I'm not interested in trying to decipher your beautiful artwork this semester. So we'll keep our rings small. And for the most part, rings are pretty small. The smallest cyclic chain that you can have is 3 carbons long. It looks like a little triangle. The root is no longer just prop. The root has cyclo in front of it. This is not a prefix on the root. This is the root. The longest carbon chain is cycloprop. 4 carbons, looks like a little square. Cyclobute. 5 carbons, a pentagon. This is where things get familiar again. Cyclopent. 6 carbons, the hexagon that you'll all get to know and love this semester. Cyclohex. 7 is truly a challenge. So if you're not feeling up for it, I don't blame you. 8 is no easier, to be quite honest. Cyclo-oct. Now I don't have the 9 and 10 membered rings up here, but they're actually not very challenging to draw. You can draw a 9-membered ring by drawing almost a complete 6-membered ring and then adding on a pentagon to the side. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. So it looks like a hexagon and a pentagon fused through one side. It's okay if you don't want to draw it. You're never going to have to draw it for my class. And a 10-membered ring, similarly, is not all that difficult. Instead, what you do is simply draw 2 hexagons fused together. And now you've got 10 carbons in that ring. So actually, the hardest ones to draw are 7 and 8. Also feels pretty straightforward. What do you guys think? So far, so good? Let's do some practice. We're going to be adding functional groups now to some of them. And what I want you to do is just determine which root belongs to each compound. I skipped over something, didn't I? I did. At the bottom there, I've got this little line that says, linear carbon chains and cyclic carbon chains cannot be counted together as one carbon chain. Either your longest chain is only carbons in a ring, or your longest chain is only carbons in a linear structure. And the best way to describe this is to look at this second example out of these 8. You'll notice that there's a 6-membered ring, there's a 1-membered group coming off, and a 2-membered group coming off. Initially, students have a proclivity to say, I'll start at this 1-membered group, count to the carbon in the ring, count through the carbons in the ring, and then count out of this 2-membered chain. And now I can count 6 plus 3, I've got 9 carbons. But will you call it non, or will you call it cyclonon? Because it's not cyclonon, and it's not non. It's neither of those, because you can't count a carbon that is in the ring with a carbon that is outside of the ring. You either only count carbons that are connected in the ring, or you only count carbons that are not a part of the ring. Seem fair? All right. If you need to copy down these molecules, if that's going to take you too much time, number these molecules 1 through 8, and just list the root come back to this assignment. It's posted on Canvas. Come back to this assignment later and fill in those molecules for yourself. Is anybody feeling brave enough to come put an answer on the board? Niera, Carly. Anyone you want. First come, first serve. Jamie?
No, you're fine. Go ahead.
He swears. I got 3 more. And I don't think they're the most challenging ones. You guys feel your heart racing a little bit? Should I go up? Should I not go up? That means you should. Are any of these surprising you guys? Good work. All right, let's just review. Compound 1, the longest carbon chain is 5 carbons long, regardless of which way you number it or kind of analyze it, unless you started from the top and then went to the left. That would look like a 3 carbon chain, which is definitely not the longest. Either a 1 carbon or a 2 carbon chain, so this one is going to be cyclohex for the 6-membered ring. Here, the most common intuition that a first semester OChem student gets is that your longest carbon chain goes straight across the board, which is not always true. And I don't try to trick my students into hiding the longest carbon chain, so you guys don't have to worry about being fooled. But other resources that you guys will explore this semester don't always present the longest carbon chain horizontally. And so in this case, we can see that the longest chain actually runs kind of diagonal through the molecule. If I go straight across, it's 6 carbons. No? 1, 2, 3, 4, 5, 6. Yeah. Sorry. If I go through this, though, I actually get these additional carbons at the end, which gives me 8. So this is going to have a root of oct. Here, again, it doesn't matter which way I go. I'm going to end up with pent. 1, 2, 3, 4, 5. Some students really struggle with counting the 2 carbons of the alkyne. So pay attention to where the lines end and where they bend. Bend, 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 end. So that triple bond ends, that's a carbon. 1, 2, 3, 4, 5, 6. Hex. 1, 2, 3, 4. Bute. 1, 2, 3. Pros. 5-membered ring. Cyclopent. Do you guys feel okay with that? That's the first part of naming a molecule. Identify its root. All right. All my beautiful handiwork. Let's move on to the next part of a name. We're going to focus now on the suffix. And I'm actually going to put in parentheses here, ES. This informs what major functional group, FG. And I'm actually going to put in parentheses, S is present. And it's important to know some functional groups take higher precedence, higher priority. So you may have more than one functional group that can be indicated in the suffix, and you have to choose. Only one of them can actually go in the suffix. The other one will have to be indicated in the molecule some other way. Now, in my opinion, the best way to really analyze this is to look at suffixes and suffix modifiers, or suffix stoppers. Things that take the suffix that's based on the hydrocarbon and modifies it. So, hydrocarbon suffixes. For an alkane, the molecule is given the suffix ane. Thus we get methane, butane, propane, ethane, cyclohexane, etc. The alkene gets the suffix -ene, and the alkyne gets the suffix -ine. But it gets fun. If a molecule contains both an alkene and an alkyne, both of those suffixes appear. And then the compound is given the suffix -ene, -ine. One thing you'll notice, ENE for the alkene drops the last E, and it becomes EN-YNE. So one thing you notice is that the EN kind of gets modified. The second thing you'll notice is that those two suffixes are listed alphabetically. E comes before Y, so the alkene is designated in the suffix before the alkyne. Lastly, alkane is never combined with alkene or alkyne. If there is no hydrocarbon, alkene, or alkyne functionality, then it's given alkane. But if there is either or both, alkane does not show up in the name. Now, our functional group suffix stoppers. Similar to how ene dropped the E to be modified by -ine, we're going to do the same thing with any of these hydrocarbon-based suffixes. We'll drop the E and replace it with a modifier that indicates the functional group. This is not an extensive list of functional groups. This is nowhere near comprehensive. And that's because we're not going to cover nearly any of these this semester. But I do want to draw your attention if I head to this free textbook, just because I know that this has got a really good resource on it. Head to the free textbook that's linked in our homepage. Come down to Appendix A, Nomenclature of Polyfunctional Organic Compounds. For one, it introduces all of the functional groups for you and tells you where to find them, reference them. And then two, it gives you their priorities. The highest priority functional group is a carboxylic acid. if that functional group is in a molecule, that suffix is given to the molecule. Everything else will have to be designated somewhere else. Then we have a lot of our carbonyls. In fact, all the way down to the ketone is essentially a list of our carbonyl families, with the exception of the nitrile that's in there. After the aldehyde and ketone, then we see alcohols, amines, alkenes, alkynes, alkanes. And then lastly, we see halogens and nitro groups. So these are things that are, they take no priority. They're never going to be the primary functional group. So coming back to this assignment, we're not going to look at all of them, but I do want you to see some of the common ones. A carboxylic acid is given the suffix oic acid. Now for better detail, this oic acid tags onto any of these suffixes. So that means we'd have something like anoic acid, for an example. You could have enoic acid. You could have inoic acid. The aldehyde is given the suffix al, which is the start of the term aldehyde, so you can see the connection between the functional group and the suffix that it has. So let's take an example where it's combined with an alkene. Now the suffix is not just -ene, and the suffix isn't al, it's -al. For a ketone, it's given the suffix -one. And you can hear the connection between ketone and -one. For example, here we have an alkyne suffix modified by the ketone suffix, -one. That's the end of the molecule's name. I've got amine up here. We're not going to deal with amine very much, and I don't think any of the examples I have amine. So I'm actually going to stop with the alcohol. The alcohol we're going to explore this semester. These other three we're not, but I just want you to have an idea. It's not any harder to go beyond the molecules that we'll do this semester. The alcohol is very similar to the aldehyde. In fact, when you try to pronounce the difference, it's nearly impossible. Al and all. And I'll give you one more example. We've got alkane stoppered by oic acid, alkene stoppered by aldehyde, alkyne stoppered by ketone. Now I'll show you when we have ene, ine, all. And I just want to make it clear that you could take these hydrocarbon-based suffixes and swap them out with any of these modifiers. You can have enoic acid, you can have inoic acid, you can have eninoic acid. Seem fair? The suffixes tell you the major functional groups, but actually they tell you two major functional groups, your hydrocarbon functional group and one priority functional group. You cannot have both an alcohol and a carboxylic acid signified in the suffix. You only get one or the other. This little activity I've got on the side, I didn't like this as much, so you can fill this in if you want, but here's methane, and the idea is it's got one carbon, that's its root, and it's got only alkane functionality based on its suffix. Propane, 3 carbons, only alkane. With 8 carbons and only alkane functionality, what root and suffix would that compound get? Octane. Only alkane functionality, 8 carbons, octane. And then we'll see something similar with alcohols. 1 carbon, alkane alcohol, methanol. 2 carbons, alkane alcohol. 6 carbons, alkane alcohol. This compound is given the name cyclohexanol. Cyclohexanol. Now let's take it back to our list of compounds and decide which suffixes go best with these molecules. So why don't you guys take a minute to try and look through them and see what you think. You want to put one up?
Talk about esters.
No, it wasn't on the list, and it's not in the set, but it's, that's not an ester. Mm-mm. It's close, but the ester has no H on the other side of the O, has a carbon group.
And the halide is never the name.
The halide will never be designated in the suffix. We obviously have to describe that a halogen is there, and if it's not in the root or the suffix, it's going to show up in the prefix.
Just be like halide or the name of the halogen.
So there is a functional class nomenclature. We were looking before at tert butyl bromide. Functional class is not IUPAC's preferred method. Functional class names the carbon chain as a substituent to the functional group. Isopropyl alcohol describes the carbon chain as a substituent of an alcohol. Tert butyl bromide. But IUPAC naming would actually prioritize the carbon chain and then use a suffix to indicate the functional group or a prefix.
Okay, so I mean, 6 just be butane.
Yeah. Mm-hmm. Well, I mean, the root would be ane. The whole name would not be butane because that wouldn't clarify the chlorine. All right. Anybody want to put some answers up? Actually, why don't you guys just give them off to me so we can keep moving. Nahira?
The first one,
A-N-E. Yep. Because there is only alkane functionality. Good. What else?
Cyclohexane.
Good. Yeah. So we know that the prefix or the root is cyclohex, and because this has alkane and alcohol functionality, it's going to get the suffix ane all. All right. What about the third one? What hydrocarbon suffix should it get? Ene. It doesn't matter that most of the compound is alkane. There's an alkene in there, which is higher priority. I guess I didn't do a good job of showing that, actually. This is higher priority, but this is higher priority. I guess I did kind of clarify that if you've got one of these, you've got to use it. So it's got ene. What other functional group will show up in the suffix? You guys recognize this functional group? Ketone. And that ketone will get owned. So this will have a suffix ene owned. Now over here, I know I showed it as kind of all together, but you can do these dashes between them as well, and we'll talk about what can go in between those dashes on the next slide. Compound 4, what's suffix? Ine. For the alkyne functionality, the triple bond. Compound 6, what's suffix? I'll give this one to you guys, so none of you have to feel embarrassed saying it. This is anal. Spelt anal, pronounced anal. because it's an aldehyde. Number 6, only alkane functionality, ane. Number 7,
Anoic acid.
oic acid, only alkane functionality, anoic acid. As opposed to enoic acid or inoic acid or eninoic acid. Sounds like old MacDonald had a farm in here. Eninoic acid. Last one. Sorry? Challenging.
Would it just be A?
Yeah. This is going to be ane because the carbon chain is this ring, and none of these functional groups are a part of it. They're all coming off of it. So that's just going to be cyclopentane with those groups coming off. Questions on this? Our priority this semester, we're going to be exploring alkenes, alkynes, and alcohols. So you're not going to have to worry too much about these priorities. And with alcohol, you're really just going to tag it on to the end of one of the other suffixes.
So do we only name the functional groups if they're part of the longest, like the parent chain?
Well, we actually defined earlier the parent chain is the longest chain containing the primary functional group. So I could give an example, let's say with this molecule, where I maybe just look at these 4 carbons, and I try to consider this not the parent chain, which is not correct, but 2 reasons why that wouldn't be great. It's not the longest chain, and it doesn't contain these principal primary functional groups, alkene and ketone. So I will actually choose a shorter carbon chain than the longest possible if it means a carbon chain that contains the primary functional group. I don't have to go with the longest possible chain. I want to go with the longest possible chain that includes my primary functional groups. All right, let's talk about locants. When you hear that word locant, is there something that it makes you think of? Location. So this, again, kind of reminds us of our regiochemistry. Locants are values. I'll try to keep it similar to what I've got up there. Locants identify where along a carbon chain a group lies. Now that group could be a functional group, or that group could be a branch, something that's coming off of the parent chain. So we're going to use locants in both the suffixes, and we'll use locants in the prefix. And there are some rules with how we decide to name them. 1, linear chains start at one end and count to the other. If you're deciding locants for a linear chain, you've got to start at the end of the carbon chain and then count through. Because you're deciding that that longest carbon chain is the root. So I've got to start at one end or the other so that I can actually number all of those positions. Cyclic chains, on the other hand, it's arbitrary where you start, so you're going to start at a group. Maybe you start where a methyl carbon is coming off. Maybe you start where a alcohol is attached. And then the last thing to know is we number in such a way that the primary functional group, whatever that highest order functional group is, has its lowest possible locant. Sometimes you can number from one direction or the other and you run into a tie. Two different ways that you could number it, and it gives the same locant set. Says I've got a group at 3 and 4 and 5 in either direction. So how do you choose which one to go by? We'll address that in a minute. So here I've got this question. Propanol, 3 carbons, alkane, alcohol. Is propanol enough information to tell you the structure of the molecule? No. I need to either call it 1-propanol, which tells me my alcohol is on the first carbon of the 3-carbon chain, or I need to call it 2-propanol to indicate that the alcohol is on the second carbon of the carbon chain. And then there's a couple of things that you'll notice there. With 1-propanol, obviously the alkane functionality isn't anywhere in specific, it's the alcohol functionality. IUPAC actually prefers that this locant goes right before the suffix that indicates the functional group. The functional group alcohol is on position 1. Locant 1 should go immediately before the suffix that indicates the alcohol. Similarly, for 2-propanol, IUPAC would prefer that this be called propan-2-ol. And there are some functional groups that you don't have a choice. For instance, you'll have an alkene and an alcohol, and you need to describe where both of them are. Both locants can't go in front of the root, so the locants should go in front of their respective suffix. So I've got a couple of examples up here. What would be the best locant for describing the position of this ketone? This ketone is called pentanone, but there are 2 different pentanones possible. So what locant is best? Well, I can either number from the left, and my ketone appears on carbon 2, or I number from the right, and my ketone appears on carbon 4. 2-pentanone is correct instead of 4-pentanone. Then I've got this other molecule, and what we're given is that the alcohol should be numbered on position 3. So what would the rest of the name look like? 1, 2, 3, 4, 5, 6 carbons. That's a group hex, suffix ane-ol. So 3-hexanol. And then the last one tells us to draw 1-butyne. That is a 4-carbon chain with only a carbon-carbon triple bond, and the carbon-carbon triple bond starts at position 1. So here's a carbon-carbon triple bond, and that's carbons 1, 2, 3, 4. There we've got 1-butyne. So far, so good? Let's apply it to those molecules again. Do I need a locant to describe where the functional group is for compound 1? No. Compound 1 is just alkane, which means it's everywhere. So there's no locant needed. What locant would go best on my cyclohexanol? Technically, because alcohol is the higher priority group, we're going to start numbering at the alcohol. I could start numbering at any of these positions, but the alcohol takes priority. That's why it's in the suffix. So I'm going to start numbering there. So we would number this as locant 1, but in reality, because we know the alcohol is the highest priority functional group, we don't have to explicitly say it. We can assume it. It's not great to assume it, so you can always clarify. Oct, in, own. Where should I start numbering? Now, here's the challenging part, and this is going to go beyond the depth of our class. A ketone is a higher priority functional group than an alkene, so I want to make sure that the ketone gets its lowest locant. Then I'll pay attention to the alkene. 4. So this is going to have a locant set of the ketone is at position 4 rather than at position 5. And the alkene starts at position 5. So this is going to have 5-ene, 4-one as its locants with its suffixes. Seem fair? We're putting them in to describe where along the carbon chain that is. What's the best locant to describe where the alkyne is here? Yeah, start from the right and give it locant 1. The aldehyde is always at a terminal position, which means we don't have to clarify. No locant needed. There's no other place it could be than at the first carbon, because that's what makes it an aldehyde. Do I need a locant to describe where alkane is for my 6th molecule? No, there's no locant here. Do you guys see the difference between no locant and no locant needed? With the alcohol, I could put in position 1. With the aldehyde, I could put in position 1, but I don't need to. Oic acid, always going to be at the end of the chain. No locant needed. That's my highest priority functional group, and it's terminal. I know I'm going to start from there. Lastly, compound 6, no locant, or compound 8. We're flying through it, guys. I hope that's okay. All right, this is the part we're probably going to have to come back to tomorrow, but I want to make sure that we've got a good head start on it because there are a lot of alkyl substituents that we're going to talk about. So let's see that we can get some definitions down here. Groups that are not a part of the parent chain and don't appear in the suffix. They still have to be designated somehow. And the nice thing about the prefix, maybe it's not a nice thing actually. They're always alphabetized. Everything in the prefix, no matter where along the carbon chain it's located, is placed in alphabetical order. Then it's followed by the root, the locant, and the suffix. These prefixes often require their own locants. Because we need to describe their position still. We need to know where along the carbon chain these groups are showing up. And then we've got this idea that if you've got a tied set of equal priority functional groups, in other words, you number from one direction, and you've got a substituent at locant 1, locant 3, and locant 5, and you number the other direction, and those same substituents give you 1, 3, and 5, how would you know whether you should name from the left or from the right? There's got to be one correct answer. We call that a tied set of locants. We give the lowest locant to the first alphabetically. This is actually a very common trend in IUPAC nomenclature. A tie goes to the first alphabetically. Aldehydes and ketone functional groups, they're often found on the same molecule, and a tie goes to the aldehyde. Aldehyde, Al, ketone, O-N-E, that's part of it. Alkenes and alkynes, when they are on the same molecule, if you number one direction or the other, and both groups have the same starting point, then you'll number in such a way that the alkene gets the lower position, because alkene comes before alkyne alphabetically. One of the most common issues we'll run into is, what if I have a methyl group and a bromo group? And if I number one way, they're positioned 1, 2, and I number the other way, and they're positioned 1, 2. Then we number in such a way that bromine gets a lower priority, because bromine comes first alphabetically before methyl. So we're going to see a lot of those in very simple cases. Generally, we don't prioritize alkyl groups over halogen groups, or halogens over alkyls. But we say that if there's a tie, we go to the first alphabetically. So I don't have enough time to give you all of the alkyl groups. We'll start with that tomorrow. We're going to look at all of the different ways that carbon groups can be attached but not be a part of the parent chain, and the names that we give them. But these other ones are pretty common. We'll see the cyano group quite a bit, but we won't name hydroxy or oxos very often. Let's just close out with these examples. What locant best describes the fluorine on this propanoic acid? Carboxylic acid is going to be locant 1, because that's the priority group. 2, 3, fluorine's coming off of position 3. So this is 3-fluoro propanoic acid, distinct from 2-fluoro propanoic acid. What locants would the bromine and the methyl groups get on this cyclohexanol? Notice that it's not calling it cyclohexane 1-ol, because it's assumed, being the highest priority functional group, we're starting from there. Then I could either number clockwise and call these 5 and 5, or I can number counterclockwise and call them 3 and 3. 3-bromo, 3-methyl, cyclohexanol. The last one, asking you to draw it, it gives you hexane al. So that's a 6-carbon chain with an aldehyde at the end. 3-oxo, that's position 1, 2. Oxo tells us a ketone. And 2 is cyclopropyl, which is just our little 3-membered ring. That's an alkyl substituent, a cycloalkyl substituent. Now, the last thing we were going to do with these molecules was just name what substituents are a part of them. And I think you guys can actually go ahead and do that on your own. So we'll pick up here tomorrow looking at these substituents and getting familiar with the other alkyl substituents, because it's going to help drive us into stereochemistry. It'll round out our regiochemistry and drive us into stereochemistry. All right, guys, have a good night. I'll see you tomorrow.